Good morning, everyone, and welcome to Recitation 3 on reinforcement learning. Last week, we saw Gantz in the previous recitation, where we generated cool images. Now, let's see how we can teach a pigeon how to read. So, as you can see, there's these instructions here, which the pigeon seems to be following apparently. So it says turn, and the pigeon turns, and then the instruction says peck, and the pigeon pecks. So how did this pigeon learn to read? That is reinforcement. So reinforcement learning draws inspiration from a number of fields like psychology, control theory, evolution, and also some ideas from computer science like dynamic programming. So far you've seen supervised learning where you're given input data X, the labels Y, and then you train a neural network to learn the mapping from X to Y, and you minimize an objective, which is a loss function, and that somehow helps you minimize the divergence between the expected outputs and the ground truth. So in this paradigm, you don't have a loss function. Instead, here the objective function is a reward function, which you are maximizing. And some terminology here, you have an agent in an environment, in an unknown environment, and there's a set of states in which the agent can be present in, a set of actions that it can take, and every time an agent takes an action from a particular state, it transitions to another state as dictated by the environment and receives a reward. So that is the basic idea behind reinforcement. That's how we formulate reinforcement learning problems. So let's learn the dynamics of the environment, which is this picture of the Earth here. So by dynamics, I mean that when you're in a particular state and you take up a certain action, what state do you end in, and with what probability do you end in the state? So one such family of methods is the Monte Carlo method, and it's a model-free method. So what this means is that you're not building a model of the environment explicitly, and instead you're simulating it, and you're just learning from experience by interacting with the environment. So how does this work? So we know that the objective is to learn the transition probabilities between states given actions, and one way we could do it is you initialize it with a random state, an agent in a random state, and you keep playing out actions by some policy, which basically tells you how to act in the environment, and you collect the set of rewards and the next states, and this collection is called an episode. And once you have this episode, you can learn based on the transitions that you observed what the state transition probabilities can be. So note that you play the episode till the very end, and that is a part of the definition of a Monte Carlo method. So what happens here is you wait till the very end for a reward, and you learn from that. But you need not just wait till the very end. You can even learn from intermediate rewards that you can either engineer into your problem, or you can guess using smart methods, and that is TD learning, or temporal difference learning. This is again a model-free method, and it combines aspects of Monte Carlo learning and Monte Carlo methods and dynamic programming. So you can, and then again, there's 2 ways you could go about it. You could learn it on policy, On policy means that as you execute the actions and you end in newer states, you learn continually from that experience, and that is the name of one such algorithm is SARSA, and or you could do it in an off-policy manner, like Q-learning, which Aishwarya will talk about in a short while. So here's a graphical comparison between the three methods: the Monte Carlo, the temporal difference, and the dynamic programming method, where in dynamic programming, you basically try to enumerate all possible set of next states, and you try to estimate the transition probabilities between them. And so far, we've seen how we learn by interacting with the environment, but we've learned supervised learning, where you provide input data, the output data, and then you learn the mapping between the two of them. Can we borrow ideas from there? So that was a question behind. So that was a question posed, and the solution to that was imitation learning, where you can learn from expert behavior, where given certain states, you take particular actions, and that leads you to good states. So that's what you see here in the supervised training data, where you have mappings from the input states to the output actions. So behavioral cloning is one such way of doing it. Again, supervised learning is one way of doing imitation learning, and behavioral cloning is an instance of that. And the data here is data collected from human performance, from human actions, or from a well-trained model in a simulator. But as you can expect, there's a mapping from particular states to certain actions, and as soon as the test distribution deviates from the training data distribution, it starts to fail. And this is called compounding of errors, where the moment you deviate from it, the state starts looking very different to the model, although to us it looks very similar. And it makes another error, it deviates further, and this process repeats over and over again until there's just no recovery. So here's a video on the same. So as you can see, because there was an initial error when this model started running, it just kept getting compounded, and it could not recover from it. So one such solution, a solution to that kind of a problem is a dataset aggregation, where you play out these actions, you collect the experience, and you have an expert look at it and tell you that this is where the model is going wrong, and suggest corrective actions so that the model can learn from the expert experience again. So here you see a picture of a person with head-mounted cameras. So the idea behind this project was that the person was trying to train a drone to fly using reinforcement learning along mountain trails, and the dataset aggregation was through the three cameras. So here you see how it works. So there's this drone that flies throughout, following a trail, and so here's where, so as you can see, if it goes way too much to the left, it corrects itself and comes back onto the path. This is because of the aggregation of data that we've done before. So the way it works is, the person, they tried it out with a handheld camera, and evaluated the network. So once the model is trained, with the 3 cameras and with the corrective actions, it can then learn to predict the next image in the scenery, where the path is, and continues following the path. So then once it's tested on the camera, you can test it out on the model, and you can see that it performs pretty well. And as you can notice, it keeps wobbling around to the left and right, probably because of the way the data was collected, and because of the corrections. It learned a policy where it could stay on the path, but it keeps oscillating between the left and right. So supervised learning is one way of doing it. Another way of performing imitation learning is generative adversarial imitation learning, which is basically using a GAN to perform imitation learning. Last week we saw Gantz, where you have a generator and a discriminator, and the generator tries to fool the discriminator, and the discriminator tries to tell apart samples which are real and fake. So in a similar way, the generator tries to predict the actions and the next state given a particular state, and it has to pretend to be an expert, to be like a human. So the job of the discriminator then is to discriminate between the actions and states of human and the generator. So that's the typical GAN setup that we've seen from last week. Here's the algorithm where you have a set of expert trajectories from before. So this means this is off policy and off policy learning. And you have an initial policy and the set of discriminator parameters. So what you then do is you sample trajectories from using the policy, and then then you update the weights based on whether or not you have a similar loss function for the discriminator and the generator, a discriminator on the left and the generator on the right, and you update the weights based on whether or not the discriminator successfully detected discriminated between the student and the expert, and whether the generator successfully managed to fool the discriminator. And you learn the Q values through a GAIL constraint natural gradient step. So these are the 2 ways you could do imitation learning. Now let's move on to value functions and value iteration and policy iteration. Okay, hold on. Just before we move on to that, let's see how GAIL works in practice. So this is a video of a lunar lander, where so this is a part of a framework called OpenAI Gym, which people normally test their reinforcement learning algorithms on, where you have an agent in an environment and you learn a policy to help the agent reach a goal. So as you can see in the initial iterations, the Lunar Lander has a very hard landing, and after a significant amount of training, it does manage to land pretty smooth and without deviating much from the initial position. So
zoom out completely. It won't zoom out completely. Yeah, now that you're familiar with some basic terminologies like the states, actions, values, and all of this, I'll just recap with some other terminology that you will need for learning offline policies and model-free policies, which I will explain. So a few things that are pretty important are the value function, the Q function, and the Bellman equation, especially the Bellman equation because it is the base or the foundation for a lot of algorithms in reinforcement learning. So when we were talking about the value function, what exactly is a value function? The value function actually tells you how valuable a given state S is for an agent, and the value function depends on the policy using which the agent performs the actions, and the value at a particular state using a policy pi is given by this particular equation, which is V of S equal to the expected value of the rewards, and it is also offset by a discount factor, because we would assume that the actions that we take in further time steps are not as important as the ones that we take immediately, and therefore we use this discount factor. And then among all the value functions, we have one optimal value function whose value is greater than the other functions for all the states, and that is called as the optimal value. And there is a policy that corresponds to the optimal value, and which is known as pi star here, which is the optimal policy. So if you look at the equations for this, this is just put in the mathematical form, whatever I said. So for a given value function, the maximum for, if you take a maximum across all the different, if you take a maximum of all these different values, you have one optimal value, and then the corresponding policy is the optimal policy, and we indicate this with stars just to say that they are the optimal values. Yeah, it's the same slide still. Okay. And all right. The next thing that we need to know is what a Q value function is. And so a Q value function determines how valuable taking an action is from a given state S. So if you remember what we were talking about in the previous slide, we said how important a particular state is. But then also from one particular state, you can take different actions. Therefore, you also need to know how important certain actions are for certain states. And that is what the Q value function tells you. And you can obtain V star S given Q star SA. And why is that? That's because if you take a maximum of all the possible Q values, you will get the V star S, because here the extra thing that you're using is you're trying to understand which action you need to take from a particular state. And the Q star SA value is equal to the summation of the immediate reward after performing an action in a given state S, and the discounted expected future reward after transition to a next state S dash. And if we know the optimal Q function, we can extract the optimal policy by choosing the right action that maximizes Q for a state S. So as we explained in the beginning of this recitation, it's very a policy is basically a mapping from states to actions. So if you know which action to take in a given state, you're basically figuring out what the optimal policy is. So if you know the optimal Q function, you also can figure out the optimal policy. And coming to the Bellman equation, this is pretty much what we explained about the Q values. If you have to find Q star SA, which is the optimal Q function, what you do is you first get the reward at that particular time instant, and then you get the discounted reward discounted value at the next few time instants, which is till the end of the episode if we consider an RL scenario. And then this we could also expand out for the expectation, where you find out the probability of going to a new state S dash given given the state S and taking an action A, and V star S, which is the value at that particular new state. And since we know that V star S is the maximum of all the Q values, which is the optimal value function is the maximum of all the optimal state functions. So what we do is we replace that in the second equation, and we get this the last equation that you see, which is v star s equal to the maximum over all the actions, the reward at that particular time step, and the discounted reward over the the discounted values over the next few time steps till the end of the episode. So this is the Bellman equation, and this will be useful when we are trying to understand policy and value iterations. They both operate on this equation. So yeah. Value iteration is basically trying to compound the optimal state value function by improving the value of v of s iteratively from a given random start value. And what we do is we repeatedly update the values of q of sa and v of s until unconvergence is found. And value iteration is guaranteed to converge to optimal values. So this is a small pseudocode of what I just explained. So it's pretty simple. What you do is you iterate through all the states, then you iterate through all the actions, and then you find the QSA values. And the equation is pretty much what we spoke in the previous slides. That is, just get the expectation and then discounted reward. And then you update the V of S. That is, for a particular state, you find the value by taking max over all the actions for the Q values. And then you do this until your V of S converges, which means that until it no further changes, you keep doing this, which means now you have the value functions for each of these states. And then in policy iteration, it's a little different than value iteration, because when I was explaining value iteration, I told you that you start from a random value function and then find a new value function in an iterative manner until you reach the optimal value function. In case of policy iterations, it's a little different, because here you start with a random policy and then find a value function of that policy, and then you find a new improved policy based on the previous value function, and then so on. In this process, each policy is guaranteed to be a strict improvement over the previous one. Therefore, given a policy, its value function can be obtained using the Bellman equation that we just went over. So here in in policy iteration, instead of repeatedly improving the value function, the policy is redefined at each step, and the value is computed until convergence. So here you're sort of giving more importance to your policy updates than your value updates. So if you look at the pseudocode for this one, you initialize a random policy, pi dash, and then what you do is you compute your values, you compute your value functions, you improve your policy based on the argmax of the actions that you get. That is, again, the Bellman equation that you have. You try to optimize that, but this time you're re-initializing your policies as well until you converge to the best actions. So all this while, we were talking about scenarios where we know how the environment operates. We know what states and actions give rise to what next states or rewards. But there can be scenarios where we do not know much about the environment. So policy and value iterations can be used when the agent has prior knowledge about the effects of its actions and the environment. And this is called as offline planning, because you know beforehand what is going to happen in the environment. But what if the agent only knows a set of possible states and actions and can observe the environment's current state, but does not know beforehand? So in this case, we go to learning paradigms like Q-learning, where the agent must actively learn through its interactions with the environment. And Q-learning is a model-free learning algorithm that does not assume anything about the state transition. Like we spoke before about what is a model-free learning. In model-free learning paradigms, the agent will not try to explicitly model the environment state transition or the reward functions. What it will try to do is directly derive an optimal policy from the interactions of the environment. In model-based, on the other hand, the agent will interact with the environment and the history of these interactions, and it will try to approximate the environment state transition and reward model. So Q-learning is a form of model-free learning. So when I was talking about Q-learning, we said that we are going to take a few states and actions. Like if you look at the first diagram here, we said we're going to pick up some states, some actions, and we're going to approximate Q values. But sometimes it might so happen that if we have a large number of actions and states in an environment, then we just can't have a table and go look at that table, both because of memory and time constraints. So the amount of memory required to save and update that table would increase as the number of states increases. And also the amount of time required required to explore each state to create a, the required Q table would be unrealistic. In such cases, what we do is we turn to deep Q learning, where we use neural models to approximate Q values. So here, instead of the table, we use a neural network that can predict different Q values for different actions given a particular state. So the input here is your state, and the Q value of all possible actions is generated as the output. So that is deep Q learning. So what generally happens in deep Q learning is that, so this is a very broad overview of what we do in deep Q learning. So the past experiences are stored in a memory buffer, and the next action is predicted by a Q network instead of having a table. And then we calculate the loss as the mean squared error of the predicted Q value and a target Q value. Now you might be thinking that what is a target Q value, because we do not have any labels. So for calculating the target Q value, we use a separate target network that can reduce the variance. And then the target network has the same architecture as the original Q value network, but with the parameters frozen. So what we do is after every, say, X iterations, we copy the parameters from the prediction network to the target network. So you have two networks. One of them is being updated every iteration, and the other one is copying parameters at, say, every X iterations. X is a hyperparameter here, which you can set depending upon the environment and the conditions that you have. So this sort of stabilizes your training and reduces the variability. That is pretty much what deep Q learning does. So to summarize, what we do in deep Q learning is we collect transitions from the environment, we train the DQN, then we select an action using the epsilon greedy policy. What is an epsilon greedy policy brings us to an important question in reinforcement learning, which is exploitation versus exploration. So we always have this confusion as to whether the agent should trust what it has already learned, or should it select a new random action in order to explore the environment and expect a better reward. So this can be controlled by the epsilon greedy algorithm, where we select a random action versus a Q value action based on a given probability, say epsilon. And then we perform the action in a state S and move to a new state S dash and store this transition in memory. So we store a memory buffer where we have all the information, which is pretty much the state, the action, the reward, and the next state. And then what we do is we sample a batch of transitions from the replay buffer and calculate the loss, like I explained in the previous slide. And then we perform a gradient descent with respect to the actual network parameters in order to minimize this loss. And after every X iterations, we copy the parameters of the actual network to the target network and repeat this for M episodes until convergence. So that is what we do in deep Q learning. There are a lot of other algorithms in reinforcement learning which use model-based or which can be model-free, and which are improvements over these algorithms that we just spoke about. This is just the nuts and bolts of reinforcement learning. There is much more that you can do. And if, I mean, initially reinforcement learning was all about gaming and stuff, but these days people have been using it in every other application, like, say, computer vision or natural language processing, etc. So if you have projects that can make use of RL, then that will be an added advantage, and we would definitely suggest that you go and look up more things about reinforcement learning and algorithms. Thank you.